Inside the human brain, billions of neurons fire in a constant, chaotic storm of raw electrical activity. For researcher Vinicius Ongarato and the Brain Systems Telemetry Lab, the challenge of reading the mind is actually a problem of isolation. How do you find one deliberate command hidden inside a hurricane of biological noise? This chart shows how fragile a deliberate signal is. We start with a steady, low-amplitude brainwave, but a simple involuntary eye blink, an EOG artifact, generates a massive 150 microvolt spike, drowning out the conscious signal. Standard AI struggles here, failing to differentiate autonomic reflexes from deliberate thought. In a high-stakes environment, that confusion is catastrophic. If you're controlling a mission-critical robotic arm, you cannot allow a facial twitch or an elevated heart rate to accidentally trigger a heavy machinery misfire. Connecting human thoughts to heavy machinery requires stripping away the guesswork. The translation system has to rely on rigorous, auditable mathematical certainty. This is the BrainReader pipeline, a 12-layer filtration journey. It starts when the frontal lobe generates a 94 Hz alpha rhythm, signaling the intent to move. That pulse hits the fast API ingestion layer first, capturing the raw, analog telemetry at extreme frequencies of up to 1000 Hz per channel. But immediately there's a complication. The clean alpha signal gets tangled with an anomalous 150 microvolt spike. The user just blinked. This visualization shows the raw data entering the DBT pipeline layer. The tangled waveform passes through digital sieves to isolate physiological artifacts. In a fraction of a millisecond, the system recognizes the 150 microvolt eye blink anomaly, logs a cryptographic hash, and mathematically subtracts it. Achieving digital command means we have to digitally amputate the body's autonomic interference before the machine even starts trying to understand the thought. With the raw voltage purified, the alpha rhythm enters layer 4, the dual Vectoria semantic memory core. Watch the chart transform. The system maps the analog voltage, exploding the 2D wave into a 512-dimensional vector space. Here, semantic matching aligns the 94 Hz frequency and dopamine triggers with a cluster labeled Reach Forward, locking in a cosine similarity score of 0.962. By turning raw electrical voltage into high-dimensional geometry, biological electricity becomes actionable machine comprehension. But even a perfectly decoded thought isn't allowed to move heavy machinery yet. It has to pass through the final security checkpoint, the governor node. This diagram illustrates the zero-trust SLRPD logic tree. It verifies cryptographic signatures, dropping delayed packets. Next, a cognitive check cross-references vector data to prove active focus, rejecting distraction. Finally, the system executes a token burn, consuming a single-use approval token to authorize the action instantly. Absolute safety in brain-computer interfaces means treating the human mind as a hostile, untrusted environment until every single parameter is mathematically authenticated. The instant that token burns, the digital command hits the physical world. The industrial robotic arm executes the instruction perfectly, locking on to the target kinematics of coordinates 100, 160, 140, 60. Because trust requires verification, the Jarvis AI assistant generates natural language logs along the way. Every microsecond of this 12-layer journey is permanently documented and fully auditable by human researchers. The BrainReader architecture moves us past probabilistic AI models that try to guess what we want. It replaces them with rigorous, fail-closed mathematical bridges. By converting chaotic human telemetry into verified knowledge, we guarantee that a stray blink remains completely harmless, while a deliberately focused thought can move the world. That is the standard for the SLRPD protocol design, secure by default.